My name is Rob Reinauer. I'm the product unit manager for the database appliance engineering group. If you have seen some of my other presentations, you'll notice that occasionally I fly under a different alias. I'm actually also product unit manager for the SQL engine group for the last 6 years, for the end of 2005 for the Katmai release and going into SQL 11. I've run the core relational engine group, the runtime environment, execution environment, threading, locking, buffer cache, the core execution engine. The fact that I now am using this title does give some insights into some of our future strategies, which I'm not going to talk about in this presentation. But at the private cloud construction presentation I'll do later this afternoon that actually has the odd name of the hypercloud, which interesting marketing interaction there. But in any case, I actually will be making some announcements in that space around what we're doing with appliances. So this is, when it was an hour-and-a-half presentation, I used to apologize and say this is sort of easily a 3-hour presentation. Now that it's down to a 1-hour presentation, I guess I should apologize again. My inclination was to leave all the content in, and so there'll be some places where I'll just skip by things pretty quickly, especially around syntax usage for some of the exposed commands. But I do want to spend a little bit more time on the principles and sort of underlying theory of how systems work, because that kind of goes to a lot of the stuff. So we talk about affinity, we talk about NUMA, we talk about cores. You know, unless you kind of have a basis, and I'm not implying that you guys don't, but wanted to make sure that we have those principles down, because everything else kind of flows from that. So spend a little bit more time there. I'll kind of whip through some of the other stuff. It's not because I'm trying to just whip through things quickly, but it seemed useful to leave the content in the slides, so at least you have it for reference later. And I'll drive in. So also, especially given that it's sort of a small room, I'm not particularly inclined to be formal. So if there's questions along the way, actually feel free to raise your hands, and we'll certainly have questions at the end. But if there's issues that seem odd or don't make sense, or you're not sure how I used a term, raise your hands. If it gets too out of hand, we'll have to move on because we're going to be moving quickly. But no need to stand on formality here. Also, there is always, when you're talking about complex system issues, there's the quandary of, do I spend the first half explaining all the terms without the context, or should we actually sort of briefly talk about the context, which means mentioning a few terms that we haven't actually explained. So I landed on let's talk about the scale-up architecture, what we've achieved, sort of the broader context, and then the second half I will drill into a lot of the principles and underlying terms. So there'll be times where I sort of whip by some terms, but we'll come back and talk about them. So quickly, what is scale-up? I'm going to talk about some of the things that we've done in 2008 R2, and I will, in a somewhat unauthorized fashion, probably talk a little bit about what we are doing going forward. A quick demo. Unfortunately, I was not able to get a 192 core box into the weight limit to fly here, and was not able to convince IBM that they should pay for shipping that baby down. So instead, we'll, I've got a video of us running on a large box, and it'll, actually it's fairly useful. And then talk a little bit about, how you can configure the system, how you can look at topologies. We'll talk about first what the topologies are, and then a little bit about how do you actually go in and make use of those capabilities. So hopefully, don't have to spend a whole lot of time here. Scale up is the ability to add resources, add CPUs, add memory, and see a reasonably proportional percentage of throughput build as you go along. Why it matters is core proliferation continues. There are, more and more cores. We're currently, a 2x8 is very common in Nehalem. Actually, 2x12 is common on the AMD side. You will see 2 socket by 24 here before too long. And I'll, just to cut the chase, the fact that I have the number there. For SQL 11, we're thinking we certainly are going to be supporting 512 to 640 cores. So core proliferation is happening, and it is a trend. and here's another term that I'll come back and talk about. We are moving towards a world where each core has its own memory bank, has its own dedicated memory bus, and has its own memory bank. What that means is each core will have very high-speed access to local memory, will have slightly more expensive access to memory from other cores on the same socket, and even more expensive access to memory that's attached to other cores on other sockets. So we're already at a hierarchical structure, although it really is local versus remote, kind of classic NUMA, where NUMA is non-uniform memory access. We'll talk a bit more about. But just to, I don't think there's anything particularly secret, although this has not been publicly announced by many of the vendors. It is the case that we're going, the logical extension of this is every core is going to have its own memory bank. I mean, frankly, I think we're going to see every core having multiple memory banks in order to satisfy them, but it'll probably still be uniform. For existing applications, when you get right down to it, scale up is a lot easier. Sort of a free ride. If the application is written well and is multi-threaded, it scales. And SQL Server is extremely well threaded. It was a decision that was made 10 years ago when certain other database vendors actually went down a path of building multiple tasks and doing their scalability on a task basis as a thread basis. SQL Server is extremely highly threaded, so it scales very well. It basically scales for free. And at the end of the day, a smaller number of servers are easier to manage. We have initiatives, actually, which fits into the whole appliance strategy. We have initiatives around scaling out across smaller numbers of servers, but there is a management advantage to having a smaller number of servers. And with core proliferation, this is just getting cheaper. So for 2008 R2, we announced support for 256 cores. We are careful to, at this point, talk about it as logical processors, and I'll go into a little more of why I'm making that delineation. I didn't used to bother, but hyper-threading is actually starting to work pretty well. So there is a useful delineation between logical processors and cores, and I'll talk about that in a little more detail. We made a bunch of enhancements in the base infrastructure. At the end of the day, none of this was really particularly revolutionary, and we won't really go into locking hierarchies. But a lot of it is, and this is not, this is age old. We were doing it back, doing it tandem 15 years ago. That as you scale up and you have resources that are suffering contention from multiple threads, from multiple logical processors, from multiple cores, you end up building a locking hierarchy. You end up building spin locks or very fast access, doesn't really matter how they're implemented, fast access locks that allow you to protect fine-grained locks underneath. And as you get more and more cores, we find we have to split, build deeper and deeper hierarchies to allow, multiple threads to access these resources underneath. And of course, we don't want a single socket 4-core system to suffer. So it is a dynamic process, at least at boot time. At boot time, we determine how many cores there are, and we make a decision on how deep the locking hierarchy should be. X events. I sure wish I could spend more time on it, but it is a mechanism that showed up in Katmai. We did some more work on it for 2008. At the end of the day, what it gives you is between 5 and 7 nanosecond access acquisition time for eventing. We actually expose it programmatically, so you can use it for performance tuning, you can use it for debugging. We use it internally for a whole bunch of other mechanisms, and we're leaning on it quite a bit more. We end up, it is becoming more and more a part of our internal eventing infrastructure, but it's actually exposed. Buffer pool, as you would imagine, talked about locking hierarchies, providing mechanisms such that hundreds of cores can access the buffer cache at the same time, not necessarily the same page, but, well, actually the same page, but not necessarily the same record. And log manager as well. There is a gestalt aspect here that shows up as you scale up CPUs and you scale up speed. Memory access time, generally speaking, does not scale up. So copying things becomes more and more expensive. I've been saying that actually for 5 years. I was saying that back at IBM and back in my youth, that copying memory is what kills you. So here it is. It's even more important. So there's a lot of work that's gone in where we can do work in place and not have to copy buffers around. Time precision, probably less of a direct issue unless you guys are doing performance work, and that getting down to essentially in the tens of microsecond accuracy. But where it actually is interesting here is the mechanism that we are using is an exposure of a counter in the Intel chipset, and actually AMD has a version of it. And what it allows us to do is, taking one of the most expensive things on a modern processor, and interestingly enough, I was also saying this 10 years ago, one of the most expensive things on a modern processor is screwing around with virtual to physical mappings. The MMU, TLB, hugely expensive, and it doesn't really scale with processor time. So using clock interrupts or any interrupted mechanism in order to do timing ends up being a very costly thing. As it turns out, it also uses quite a bit of power because this ring transition, going kernel mode to user mode, having to flop the memory management unit mappings, potentially screwing around with the TLB, very expensive. So there is a capability that was exposed in Windows Server 2008 R2 that allows us to have a user mode counter, basically. And so now we can do time granularity and scheduling without ever going to kernel mode, without going to ring 0, which doesn't seem like that big of a deal, but we got about a 20% savings in power utilization, which is wild when you think about it. That it just shows how sensitive those ring transitions are if you're doing it on a regular basis. So going up to 128 processors, and this is a place I won't spend a whole lot of time talking about because we've published those numbers. So these are out there. You can get access to it. There's restrictions about how much I can get creative in talking about these, and that it's part of the Transaction Processing Council mandates. But these reports are out there in a whole lot of detail, and we could spend a lot of time talking on it, but this is something I've got some links to, and it's easy for you guys to see. But at the end of the day, we're scaling very well up, actually to 192. The numbers that we published are at 128, but we're getting above 70 to 80% scale, including I/O, including a full executing system environment up to 192. So I'm going to try a quick demo here, and let's see how our display system works here. There are odd complexities, and there we go. Nice. Although it's not showing here. Doesn't matter. So this is a 192 core system that is running in Redmond. It's Intel Athena. It's architecture. It's I think a 3950 with three subsystems put together. But what we're showing is a load driving a number of users that was calculated to sort of drive a 64 core system, which is we're running 64 cores right now. And in this case, it actually is cores. Hyper-threading is turned off, so it literally is 64 cores. And what we're going to do here in a second is add another 64 cores to the system. And what you would hope to see, if it is a valid run, you would expect to see the load drop by around 50%. We've now got twice the capacity. And we will then, which is what we just did, Madan clicked on our little tool here, which actually is a demo tool put on top of Task Manager. So it kind of looks like a full demo tool. The reality is that bottom part is Task Manager, and the top is our little driving tool. Now, we're going to click here in a second and double the load. So we're going to add twice as many users, and you should see it, pick up the capacity. You'll see the load utilization jump up. And there we go. So we're now driving twice as many users, and it actually literally is twice as many users, on a 128 core system. Xeon processors, non-hyperthread. And we will let this run for just a second or two, and then we will add another 64 CPUs. And this time, we're not going to run as well because we're short of time. And we will then add another 33% users. And again, you'll see that it pulls the load back up. And what ends up being most interesting is adding the users. And there's a brief spike, but we're not going to wait. Yeah, good. So clicked on the users. So we now are running 3 times the users, 192 cores, and for those of you that use Task Manager for performance monitoring, you can see that actually that interface is maybe becoming limited as a mechanism to do detailed performance analysis on a system. It actually, we're thinking we'd like to build this into a screensaver of some sort, because it's certainly something to see. So let's get on to the actual terminology. What are we talking about? So I talked a little bit about logical processors, threads versus cores, and I'll talk a little bit more about hyperthreading in detail. But previous to, are there any Intel employees in the room? Okay, so not to just hyperthreading, but previous to the 5500 series, previous to the Itanium family, we did not see that much performance benefit coming out of hyperthreading. I mean, there was some, but it wasn't particularly significant. And generally, given that our scheduling understands the actual thread level, it understands that the kernel, that the operating system is scheduling threads on those cores, and that at some level, Windows, even though maybe in its heart of hearts, it knows that it's a hyperthread as opposed to a core, it can confuse the scheduler. You can end up having odd scheduling phenomenon where you think you have more cores than you do. And so often we would just tell people, you should turn hyperthreading off. At this point, I think that's changing. We're now saying you should turn hyperthreading on. It really does make a big difference. And so I'm now much more careful to delineate between logical processors and a physical core, because often it's the case you'll have 2 hyper-threaded threads per core. So we'll come back to that a little bit, but hyperthreading actually is starting to really rock and roll. When I say core, I mean you think it's a die. When I say core, I mean a die, an actual CPU silicon entity. Certainly there are multiple cores per socket, so don't think of it in terms of the processor, but it is that die on the socket that is a CPU, which contains potentially multiple logical processors, using hyperthreading. When we say socket or processors, you might imagine it is that little chip that you've actually seen, that if you're a hardware-oriented person, that you've plugged in. It is literally a silicon thing with little pins on it that you plug in, which has multiple cores, which are hyperthreaded, which is what I'm trying to convey with our little encasing with encasing with encasing. A NUMA node. Well, actually, so NUMA in general, I already talked about this a little bit, but it is one of the fundamental enhancements and places that we have been working, really since 2005, in order to get big scale on a Superdome, and then these days to get big scale on a 2-socket system, because everything is becoming more and more non-uniform. As I sort of alluded to, we are heading towards the point where every single core has its own address space, which means every single core will have, very fast access locally and uncontended access locally, that he can get to that memory without other CPUs bumping into him. He's, at least with minimal CPUs bumping into him, and that's if we do a good job. And, more expensive going to memory that's attached to a separate core, even more latency when going to memory that's attached to a separate socket. So that's a pretty important characteristic. And it's not just a big system thing. When we talk about NUMA, and I know I'm repeating myself here, but it's important. We are not just talking about 128 core systems. If you buy a desktop with 2 sockets, that baby's NUMA already. So everything is becoming non-uniform at this point. And it's, it just comes down to how many CPUs can you feed from a single memory bank. And even to the point that, it is, you don't even have to build a very complex model to see, actually, I can't even feed a single core from a dedicated memory bank. And even that is actually, it's happening somewhat, but it will certainly out in the well, I shouldn't reveal roadmaps, but a couple of years from now, it will absolutely be the case that you will even see separate memory banks per core, and that you'll have to, and if y'all are familiar with banking, and that you have, say, 4 arrays of memory, you strobe all 4 of them at the same time, and you have to wait for a full memory latency before you get any data back. But by the time you get that first cache line, and that's typically how it's doing the fills, you do a fault in the cache, and the cache then is pulling it in from memory. By the time you've waited for that first memory bank to come back, the other guys have their data ready as well. And so you end up, in effect, getting them for free. And so it looks like a single memory latency access time, but the reality is there's banking going on. So, we are becoming NUMA in a big way, and it's something that you're going to actually have to start thinking about. And I'll talk a little bit about how we expose that, how you can see the topologies, and we've made it fairly easy to be able to modify affinities and such if that is useful, if it's needed. So a NUMA node then is at the moment, and this will be an interesting conversation a year from now because I'll probably talk about a NUMA node a little differently. But at the moment, consider a NUMA node to be a socket. That each socket is going to have its own memory banks. You don't have to worry whether it's multiple memory banks. Each socket's going to have a set of memory, at least. As it turns out, actually larger systems, especially older, I'm now mixing old and new. Certainly some of the older boxes will have multiple sockets, multiple processors per NUMA node, per memory core. But that's passing. We're getting very close to the, where you'll actually see every single socket, actually it already is the case, that every single socket has its own NUMA node, that has its own memory address space. But in Management Studio, we actually provide the ability to see, because sometimes it's not even obvious reading the specification of a box. Well, how actually is the memory partitioned across sockets? And so we make it pretty easy in Management Studio to sort of show the topology and show how many NUMA nodes are there and how many processors actually live within that node. Group is a new concept. And I am the first to say there has got to be a better name than group. But that's what was picked. It wasn't actually this, well, that's what we picked. So it's not the most exciting marketing name, but a group is a collection of 64 logical processors. And there's historic reasons why that's the case. And as a result, in say a 128 logical processor system, that might actually be a 64 core system, which might be 32 sockets, dual core, hyper-threaded, getting you up to 128. You'll have two groups. And by default, it's going to try to evenly spread them between groups, and it's going to, and it always obeys NUMA boundaries. So you never have a group that crosses NUMA boundaries. So, and this gets configured at boot time. There is an aspect here, and I'll probably go into it somewhere further, but it's worth mentioning now. By default, actually not by default, it is just the case. Existing applications, including SQL Server 2008, SQL Server 2005, any application that has not been explicitly modified to run on greater than 64 logical processors will run within a single group. So without modification, existing applications will only make use of 64 logical threads, and that's an aspect of Windows scheduling. It turns out, from our point of view, we don't care, but it's the way that Windows exposes this, and it really shows up explicitly. If any of you have messed with affinity masks, that it's like very explicit. It's got 64 bits, a 64-bit word, and each bit shows whether or not there's affinity scheduled for it. It's a fairly straightforward process to modify an application to run on greater than 64 logical processors. There's really two ways. I don't think I actually talk about it in this, and I probably shouldn't get carried away and talk about it too much even. But when you create a thread, you can specify a group. So any place that there's thread creates, you could actually say, actually run this within group 1 or run it within group 2. You can also do an explicit operation that after threads are created, you can assign it to a group. So it is happening generally around when threads are being created, and before you've dispatched it into a code segment, you're typically saying either create time or right after the fact, hey, run on this group or run on that group. And that is the work that we've done for our 2008 R2. As you can imagine, given that we've got a fairly modularized code base, it really was not much work at all. As a matter of fact, it was well nigh trivial. But the work actually ends up being, okay, what do I have to do to make my system actually scale at that level? And that is where all the work ends up going on. So questions on this? This is sort of kind of the, I know I whipped through it pretty quick, but this is sort of the core underlying basis of, really all of the scheduling scale mechanics of system scale in general, performance analysis even. Okay, I will take that to mean that this has been a completely clear and well communicated set of terminology and everybody completely understands what we're talking about. Or that it's still early in the morning. So to touch a little bit on hyperthreading, what actually is hyperthreading and why was it an issue? Why has it had problems? The reality is a processor, every time I hadn't thought of it, it's actually very similar to the principles of memory banking. It's the very same thing. It's pipelining. So every time, if you start an instruction stream at some arbitrary time, it turns out on that first clock tick, the CPU actually is not executing your instruction yet. The first thing he does is he says, where do I get my instruction? And then the next step, he then says, oh, okay, go get the instruction. And then he decodes and says, well, what is it that I got? And then he, looks at it, especially if it's a branch, there's a whole lot of interesting logic around where am I going to jump to? And that ends up being, there's a huge science, ton of research is being done around branch prediction. And actually, here's where I'd be comfortable having the Intel guys in the room. Intel has just done miracles in that space. It is actually ungodly how well they do their branch prediction now. They have a branch prediction cache. They typically fetch both paths. They sort of assume, let's just assume either one of those guys could happen. They prefetch them. They have targets. They are keeping track of, at this point in the code, what did we do last time, and use that as part of their frequency analysis. It's really astounding how well they do. Because this has traditionally been, this was sort of what led to RISC processors being so popular. Because you weren't so pipelined. And you were, running, single and almost running instructions per clock. In a deeply pipelined system, which is, what you had certainly mainframes and mini computers, and Intel's kind of always been in that camp. Pipeline stalls are what kill you. You could easily run, if you're not careful, each instruction takes the total number of pipeline stages to actually run. If you guessed wrong all the time, you would literally be waiting for, and this one, 1, 2, 3, 4, 5, 6, 7, probably 8 or 9 cycles per instruction just to get that guy through the pipeline. So you will see that so really what hyperthreading is doing is saying, well, let's have 2 sets of state. And really all hyperthreading is, when you get right down to it, is I'm going to keep track of 2 threads. And that way, if one of them gets blocked, I got the other guy, and I'll let him run through. And blocking could be I guessed wrong in a branch, and I thought it was going to go that way, and I've got to I've got to start fetching a different set of instructions and let them go all the way through the pipeline, which has actually become much less of an issue. It could be I'm referencing a variable that is behind me in pipeline, for instance, and I have to wait for that thing to catch up so I know what it is to do a calculation on. That's actually pretty common. If you've heard people talking about out-of-order execution inside CPU pipelines, and actually the optimizer, often the compiler, is doing a lot of this work. He's moving things around and trying to make sure, even renaming registers, so that somebody who's referring to a register that actually somebody else is going to put a value in, that he'll actually rename the registers and give them separate ones so that they can run in parallel. So there's a lot of tricks to kind of get around the pipeline stalls. But in any case, there are stalls. Hyperthreading just says, well, I'm going to have a couple of guys running at once, and if somebody gets blocked, I'll run the other guy. And it just allows you to use the resources. And certainly it is a sign of things to come. I was about to point at the screen here. And because of this room, this is going to be, well, I was going to point at the screen. I'm not sure that I can physically point at all the screens. But if you look at the ALUs, you can already see that there's a whole bunch of parallel resources already being made available in the CPU. And so I think the writing is in the wall. You'll certainly see greater than 2 levels of hyperthreading coming along. And even, well, I haven't seen this in official presentation, so I can't possibly be giving anything away. The whole nature of core versus socket is something that almost certainly is going to go away. That you're going to start seeing these things just built into the motherboard, and you're going to have, baskets of ALUs, baskets of prefetch units, baskets of branch prediction that are all, sort of in a loose confederation. But for the moment, this is what it looks like. So talked about NUMA a bit. This is the, sort of a graphical view. And I apologize. There are, in going to the wide format display template, I think there's going to occasionally be some odd little display artifacts. So forgive my PowerPoint. It actually looked really good before things moved, but there's some odd things here. But in any case, this is a 2-socket quad-core system. Or actually, it's two different 2-socket quad-core systems. The top one is a pre-Nehalem, pre-serial memory attached bus architecture system. So does anybody know what the name of that single memory bus is in that top system? Infamous name. It's what people refer to as a front-side bus. So it's a single shared bus. All of the CPUs, all of the logical processors, all the cores are competing for that single set of memory over that single bus. Now, the reality is that memory is probably banked, especially in the end of, right before the 5500 series, right before the Nehalem architecture, but before they went to a serial attached memory, which Quick Connects, Intel calls it, Hyper Channels, AMD calls it. It wasn't uncommon to have an 8-way banked memory subsystem, where you would actually have 8 banks of memory all being strobed in order to try to get around this whole memory contention issue. But you can only go so far. And frankly, the fact that Nehalem is as much faster as the previous processors, some of that was some of the core speed, but most of it was actually this. Most of it was they finally just gave the cores access to enough memory. In the bottom picture, this is a Nehalem or any of the modern AMD chips. Again, 2 sockets, 4 cores, hyper-threaded. So actually, there are 8 logical processors per socket, and each socket has its own set of memory. And so as a result, those 4 cores, 8 logical processors, are feeding off one memory, and the other socket is feeding off the other. And so you spread the contention out. And you could see that it's not much of a hop to say, well, boy, how about if I just added a few more memory arrays per socket? It just cuts back on the contention even more. And especially as CPU speeds ramp up, you'll see more and more of that. Any questions on this? This is another this is my explanation of NUMA diagram. And it's a fairly important sort of fundamental architectural view. And leads to why we talk about a lot of the affinity issues we're going to talk about. Okay? Must be a very high quality drawing. Processor groups, already introduced. Collections of up to 64 logical processors. You cannot split NUMA nodes across groups. The processors are numbered sequentially. As I mentioned, legacy apps always run within a single group. You can actually use affinity to specify that. So you actually could take, the limitation is that the legacy apps will run within a single group. But that doesn't mean you can't have multiple groups running. So you can certainly take, for instance, SQL Server 2008 and use affinity masking to say, hey, for this instance, I want all the threads to run on this group. You would actually do it at the NUMA level. You would, it would take looking at the topology in Management Studio, and you could then just say, I want this instance to run on these processors, that instance to run on that processor, and then in effect what you've done is allowed different SQL servers to run within different groups. But each instance is going to be limited to 64 until you get to 2008 R2, and obviously from here on, SQL 11 on, it will always be set up to transparently use all of them. I've mentioned affinity a couple of times, sort of blew past it, but fundamentally affinity is the ability to, within an instance, say, I want my threads to run on this processor. Fairly straightforward concept. We did make it the easiest thing to do in the past. It was a system stored procedure that was a bit obscure. We now have exposed that through DDL. It's exposed in a quite a bit more visible fashion inside Management Studio. Generally speaking, auto is probably the right answer. We do a really good job of figuring out where instances should run and scheduling them across cores. There is a long time mirage of trying to tweak cache affinity. When I was in college, people were writing research papers on cache affinity, and surely if we schedule threads on the same processor, we'll get better cache affinity. Absolutely the case. You absolutely do get better cache affinity. Nobody has found good results, frankly, till now. Even now, I mean, still, there's an amount of work to do to make the affinity happen, and often by scheduling threads on one processor, you do get better cache affinity. And cache hit rates, you get better cache efficiency. But almost inevitably, you're leaving other processor resources unused. And so the research shows, and maybe some of you all already looked at it, people have been trying to prove this for 30 years, which reveals a bit about when I went to school. And nobody's really found particularly good results. In some of the really high performance, where you can kind of specialize, nail things specific, in very fixed workloads, you end up seeing some benefits. But that's very, very hand-tuned, artificial. And it really gets down to it, generally speaking, don't think that cache affinity is something that you're trying, that cache locality, cache affinity is something that you're going to be able to do a better job at. It just, although I'm sure people will argue with you for hours about it, but I promise it is one of those things that just never ends up quite working out. So I mentioned that we have exposed a topology view inside Management Studio. It's down under the instance properties, and it will expose the NUMA nodes and expose the processors. So you can actually see here's what the topology is. It may not be obvious what the actual NUMA architecture is. It's set at boot time, so it doesn't change over time. But on each, it generally doesn't change across boots. But it is generally speaking easier to look here than trying to look at the data sheets and figure out how it was organized, because sometimes it's not intuitive. We'll go through this pretty quickly. You can now do, and actually I should have mentioned that certainly there is a very easy way to set affinity here also, that you can actually, you're on a per instance basis. So for each instance, you're inside Management Studio looking at that instance, you can set the affinity by core here. You can also do it through DDL, and so we have moved away from, and I think we're actually deprecating the spconfig options that allowed you to do it that way, that were certainly unintuitive and led to all sorts of unexpected consequences when people got themselves in trouble. It's quite a bit more explicit now, easy to understand. This is all documented, by the way. I'm not spending a whole lot of time on this, but tons of documentation online on this already. Same for finding out what the affinity configuration is. As it turns out, I cannot make the statement that this has become a whole lot more easy to use and intuitive, and that it still is a big bit mask, and you have to sort of understand where the pieces are. But we expose it through DMVs. There's code fragments. It's very well documented online. Same with current affinity configuration. If you're not sure whether it's in a manual versus auto mode, easy to tell. So, really, reasons to change affinity. Generally speaking, the only time you'd really want to make use of it is for consolidation, in my opinion. And I run performance groups in SQL. Actually, the performance group is now moving under me this week, even though I have tried to get away from performance for the last several years, but I'm back to it again. The consolidation is really the one that matters. The cache affinity piece, you will almost certainly not end up coming out ahead in the grand scheme of things. The interrupt rates is an actual real issue, but it's unlikely it's something you have to worry about. You can imagine, if the way that interrupts are fielded is generally some unwitting thread just gets picked as a victim from kernel mode. The kernel just says, just pick some random thread and says, hey, run the interrupt for me. And it runs in the context of that thread. Obviously, if that thread is running on a different NUMA node versus where the device driver or code is, you could have some very bad effects. But that generally does not happen. Unless you're running benchmarks on really large systems and you're hand coding things and hand crafting the location, generally you shouldn't have to worry about it. We do a very good job, we being us versus us in Windows, in the way that we schedule the async I/O and the way that the IOs are being, the interrupts are being fielded. It will almost always do a better job of running on the right NUMA node than you would be able to do by hand placement, unless you really, really are kind of handcrafting a very sort of artificial environment. Even to the point that we clone pages, and we'll do more of this in the future, but we literally will copy, multiple portions of our address space into other NUMA nodes so that they get local access. And so consolidation, though, real example. Now, yeah, I already talked about that. So here's an example. For instance, I've got, which is actually a very odd system, that a 3-socket system, but it displays well. And that I want to have one instance with 8 logical processors, and I want 2 other instances, or for that matter, maybe one of those is analysis services. And I don't want them competing for resources. I don't want buffer cache contention. You could certainly define, it would make sense perhaps, to define affinity across these, so you're, of this 3 instances, I am specifying each instance to run on a set of processors specifically. As it turns out, and it is what I will be talking about at 1:45 this afternoon, we actually recommend using virtualization. And so for consolidation, virtualization is the route that I sort of announced to you. Actually, I was standing right here a year ago and said, you should be using virtualization, using Hyper-V for consolidation. And what I'll be talking about this afternoon is building private cloud infrastructures using Hyper-V and virtualization to get effective consolidation and resource utilization. But Hyper-V only supports up to 4 logic processors at the moment. So there may be a window where, for instance, I need to have 8 or 16 or 32 cores on a given instance. Well, then this would actually make sense. There is also a subtlety around specifying max memory, and that there is an advantage if you're going to use affinity, specifying max memory, because that will specify, and making sure that it is the amount of memory on that NUMA node, because then you make sure, for instance, if you don't, you actually could easily end up with, I specified 8 cores on these CPUs, but the buffer cache is growing and shrinking, and he's using local memory, but sometimes he's using remote memory, and you're getting contention with other nodes, and probably non-deterministic execution behavior. So that's, if you're going to use this and sort of nail things, you also ought to nail the memory too. And don't specify an amount of memory greater than the size of memory in the NUMA node, because you will get memory from other NUMA nodes, which will guarantee that you've got sort of odd latency issues going on. Talked about this. There actually is a tool that we have. I've provided a link to it. Not that it is rare, I think, that you will have to worry about this. But we do provide a tool that allows you to nail interrupts to processors. Actually, as much as I've talked about how you shouldn't do it, I arguably shouldn't have the slide here, and I shouldn't include the tool. But it is there, and it is a valid mode for very, very large systems. There's also an aspect around, I want to partition a system, and I want to do it in a way that is not an even multiple of the number of actual NUMA nodes. There is a capability, and I provide a link to it. It's from a guy, Slava, in the SOS group, that does talk about how you can actually synthetically say, for instance, if I've only got 2 sockets, but I want to run 3 loads and have them partitioned, there's times where it actually makes sense to make the system think that you've got 3 NUMA nodes. And so it's what we call soft NUMA. It's somewhat esoteric, but interesting reading. So that was, I think, certainly a whirlwind trip through system architecture, scalability, hyper-threading, NUMA, cores, logical processors, affinity. So 2008 R2 scales up to 256 in a moderately unauthorized statement. not to represent a commitment by Microsoft or any of its subsidiaries worldwide. We will almost certainly be supporting 512 to 640 cores out, in our next release. It really depends on where the industry goes, what systems become available. Because actually, at this point, we're not limited. The 256 is only because that's all the hardware we could find. We could have, if there had been 384 processor systems, we could have easily supported that. That's just what there's available and what we've tested on. So going up to 512 or 640 is really not going to be a particularly big deal for us. It's mostly testing. Might have to tweak some of the page. Almost certainly, actually, we'll tweak some of the page cloning algorithms, where we get more and more aggressive about duplicating memory. What we'd actually like is for it to happen in hardware. We'd really like to have hardware provide transparent cloning so that it happens through hardware. But in any case, we'll be supporting larger processors. Shouldn't be a surprise here. You will only be seeing more and more cores. The days of single-threaded execution are long gone. The world's becoming NUMA. If you haven't been thinking about NUMA and you're involved in performance or scale or system architecture, you ought to be thinking about it, because it is the case that memory arrays should be assumed to have non-linear latencies across them, and it's just going to get worse, or better, depending on how you look at it. Existing applications will scale up to 64 logical processors, which is a group. We have made the affinity specification quite a bit easier through DDL. No longer do you have to do the SP config and sort of learn obscure syntax. And really, consolidation is where you should be thinking about affinity. And it's certainly not cache locality. And even the high I/O interrupts, I think, is pretty rare. So I have some additional links there that are in the presentation. If you are of a hardware bent, not to expose my biases and strange obsessions, but damn interesting reading. So, questions? Gotta be questions. Yes.
At what sort of level is that? I've got lots of clients who are either feeding and just put it tumble, but they're not running at an agile level yet. I mean, is that sort of level?
Yeah, starting with the 5500. So the question was, where is hyper-threading coming into its own, and where does it become relevant? And I assume that there's an underlying question of what are we actually talking about when we say relevant. So starting with the 5500 series, with the Nehalem 4 cores, and certainly including the 8 cores and the 6 core variation of the 5500. And we are seeing, whereas before we used to talk about 20, 25, maybe 30% on a good day, I think you often now see greater than 30% up to 50%. And it's going to only get better. Other questions?
Related to that, is this NUMA type architecture also coming in with Nehalem?
Yes. So the question was, did the NUMA architecture come in with Nehalem? On the AMD side, and actually I don't really remember where it first started, but it's been around for a while. AMD went there quite a while ago, years ago, frankly. And any system that's using hyper transports, on AMD, that means it's a NUMA architecture already on a per socket basis. For Intel, it started with the Nehalem series. That really was the big innovation for Nehalem, was introducing of the Quick Connect system, which is a high-speed serial attached memory bus on a per memory bank basis, or on a per memory a memory set basis is a better way of saying that. So it was on the Intel side, it's with Nehalem. And not to take away, certainly the core of Nehalem has some improvements, but not the level. I mean, we are, again, not that this is a commitment towards performance by Microsoft or any of its subsidiaries worldwide, we're seeing like 2x improvement going to Nehalem. I mean, it's just crazy. When I first saw the results, there's ridiculous. You can't go to the same processor at the same speed and see twice as much. It just doesn't happen in this world. It's just crazy. But we're seeing on SAP benchmarks that are, including I/O, that it's a balanced system, so we're tuning the whole system, but literally about 2x. I mean, it's crazy how much of a difference it makes. And it's not just the core. A lot of it's the fact that you've got parallel access to memory. What else? Pipelining? Latency issues? People with questions about Exadent. Yes. That's actually a good question. I should have included that, as a matter of fact. So it is the case now with Hyper-V, and the question was, what are the implications on virtualization and Hyper-V when you're talking about NUMA? So at the moment, Hyper-V and VMware largely do not support full demand paging on their memory spaces. You allocate a chunk of memory, and that's what they have. It's a static chunk of memory, and that's what they execute in. It is worthwhile thinking about the sum total of those virtual machines ending up being something that will fit within a single NUMA node. So Windows will do a good job where it can of allocating those within separate NUMA nodes. And Windows does a very good job. A lot of the work that is going on around the NUMA scale, Windows is doing the work for us. It's not that SQL is doing all the work. We do some page cloning, but Windows does a lot of the heavy lifting. So where it ends up being problematic is if, for instance, you've got 16 gigs on a NUMA node and you allocate, 3 7-gig VMs, you likely are going to have some NUMA crossing going on. So there is a little bit of being aware of it. Being aware of what do the NUMA nodes actually look like, and making sure when you're allocating memory to virtual machines that they end up being in quantums that will fit evenly between them. And given that there's available memory, it'll actually do a very good job. It should not end up being an issue, but you could certainly, if you're trying to use every last piece of memory, and you could create situations where you will end up having some NUMA crossing. It's a point I ought to put in here. As a matter of fact, it's really it's something that I actually will expose, now that I think about it, in the SQL 11 timeframe. Not this is a commitment on features by Microsoft or any of its subsidiaries worldwide. But actually, I think that it would be useful having that exposed as a visual sort of in the instance thing too. Because there is, not to jump ahead to my presentation this afternoon, the virtualization, this ability to have a ring -0, which is kind of how virtualization works, base level, and second level address translation and IOMMUs, which is what gets rid of the overhead that was going on with virtualization. All the MMU memory, physical to virtual memory translation is a very expensive process. And once we got to fully dedicated MMUs, that was, most of you probably weren't even around back then, but it really changed how virtual memory systems, suddenly there was no question about running virtual memory systems. It just became a non-issue. So having to run some of that in software is just horrible. I hate even thinking about it. So that capability is now built in silicon. So really you should start thinking about, it's almost the case now, it will certainly be the case within a year or two, you will not be able to run on a modern processor without being in a VM. Now maybe you only have one VM per box, but you're going to be in a VM. That level of isolation, virtualization, the second level translation between page faults, virtual to physical translation, and the DMA mapping that again has to happen in a embedded 2-level mapping. That's happening in hardware now. For that matter, if you look at the page tables in Windows 2008 R2, they're 2-level page tables. They're already built assuming that there is, in essence, a virtual machine. So, it will soon be the case that there is nothing, you have no choice. Everything is in a virtual machine. Now, you may choose not to have multiple ones on one box, but it's going to be like virtual memory. So actually, when you think about it, virtualization, it really is just an extension of virtual memory. And nobody gets hot and bothered about virtual memory anymore. The fact that we're using demand paging and separate address spaces and that hardware isolation, people just take that for granted. The moment there's a certain religious concern around virtualization, but when you get right down to it, it's just an extension of page memory. It's just an extension of virtual memory. That was an awfully long answer to that question, but getting my opinion in there. Other questions? Sure.
Should you
So I'm not, tell me if I got the question right. So you're saying that normally you would have separated the SQL Server instance from the application and putting it on its own server? So I think it's really an architectural issue. it will certainly be the case, it's almost always the case, that you will get better latency behavior if you have two applications talking to each other on the same system. So whether you're using virtualization or you're using affinity, you can certainly build that resource isolation in so that they're not bumping into each other. There's another subtlety here when you think about it. We're not too far away from, you're not going to be able to buy a system. Unless you artificially constrain it, you're not even going to be able to buy a system that has less than 24 or 32 processors. And they're going to be fast. They're going to be Nehalem class processors. Are there any AMD employees in there? It's probably being filmed. So I assume they will achieve some form of parity. That that they will get back to a much more competitive playing field. I think it's just inevitable that we view a single system as supporting multiple applications running on it, whether it's multiple SQL instances, whether it's, it's part of what I'll talk about this afternoon is, viewing each application that's being run, each data tier componentry, which we often think of as a database application, but the sum total of database files, user IDs, encryption keys, all the stuff that sort of lives on a database to support a given application. There's a real advantage to having each of those in its own virtual machine. And so, you almost stop thinking in terms of, I'm going to have one instance on a box that supports a bunch of applications, and moving more towards each application gets its own dedicated execution environment, because there's essentially no overhead from a performance point of view at this point, which I'll be talking about this afternoon. And there's a lot of advantages around billing, metering, SLAs, configuration isolation. You end up having this pristine execution environment, and you can move around. You can use online migration and keep it on, literally move around very easily, which is, if any of y'all have tried taking the existing instance and moving it to another box, it is a non-trivial process. You have that guy running in a virtual machine, it's a non-issue. You can actually do it without any downtime. We won't even drop connections. So, not only is it the case, I think, that, and it's not really my opinion here, just you can just do the math, that a given box is almost certainly going to be carrying multiple loads just because of the capacity that a box will service. It really, even I think, you start thinking in terms of each application, each database application gets its own instance and its own OS and its own little dedicated execution environment that then can very easily fail over, can move around, can be load balanced, can be paused, can be put on the shelf, if it's not going to run for a couple of days, and then pick up right where it left off. That, something you can't do with existing systems. So that was perhaps a longer answer than you were looking for. Other questions? We might actually finish right when we're supposed to finish. Okay? Well, thanks a whole lot for coming. And there's a related session.